Okay, let's start today's session, and we'll start with the talk by Tony Pantev from UPenn, and the title, as you can see, is the Pushforward Theorem and Applications.
Thank you very much. What I'm going to talk about is this joint work in progress with Dima, Arinkin, and Bertrand Toën, where we are trying to understand the symplectic structures relatively on families of spaces which vary with parameters which are in a topological space. So we have some sheaves of spaces which typically are going to be moduli spaces or moduli stocks, and we're trying to understand what would it mean to have a symplectic structure along the fibers of those sheaves, and to construct such structures and use them in some meaningful way. And I'm going to show you there are various applications one can do. In particular, there are interesting applications to topological Fukaya categories. But I'm not going to talk about those applications. I'm going to show you a different set of applications about constructing Poisson and symplectic structures on the moduli as Stokes data on a smooth variety over the complex numbers. So somehow the talk has two parts. One is some general theory which gives you a way of thinking of symplectic structures relatively and tells you how to construct them. And the other is trying to use this deep machinery and do computations and get some interesting examples. But yeah, it's a bit heavy on details, so I've tried to trim it down, but it's still a lot of stuff. We'll see. Okay, so here's the problem. What I want to do is I want to start with sheaf F over sheaf F over the topological space S. And one thing I want to know about this sheaf is I want to know that the fibers are some kind of geometric object. So they're going to be for me stocks or in fact derived stocks. And I want to understand what it means for such a sheaf to have a symplectic structure on each fiber. And so for this to make sense, you need the sections of your sheaf to be geometric too. So you need them to not just be stocks or derived stocks, but you need them to be algebraic stocks or analytic stocks. Something that has reasonable geometry. And the other thing you need is when you're specifying a relative form, so there will be two pieces of data, the closeness data for the form, but you also want to specify a non-degeneracy condition for the form. And now, because we're dealing with a sheaf whose stocks can jump from point to point, the non-degeneracy condition cannot be naive. It cannot just say, oh, my sheaf has the property that, my form has the property that on each stock it's non-degenerate. What it will have to do, it will have to involve somehow duality on the base, which parameterizes the stocks of your sheaf. And so it has to be some reasonable topological duality for sheaves of vector spaces on the base. And of course, the most natural one will be the duality. Yeah. There will be an example. There will be many examples, but yeah, there will be. Just be patient. Okay. So let me just recap this. I've talked about, in fact, in this conference many times about symplectic structures. I don't want to spend time on that. If you haven't seen it, you're not going to get it anyway from the first pass. But maybe you'll get some idea of what's behind it. So what are we talking about? So say that we have a geometric object, which I'm calling F here. So it's an algebraic stack or space, which also has some interesting function theory. So it has differential graded algebra functions. The functions have these extra nilpotents that sit in different homological degrees. The reason you care about those things is because they actually come to you naturally as solutions to moduli problems, and also very often, if not always, if you do it correctly, actually resolve singularities of moduli problems. So you need to keep these guys as part of the data so that you're not dealing with singular spaces, and once you have them, you can ask what a closed form on such a guy is, and you get a little bit of extra complexity here because, so there is a complex of closed p-forms, algebraic closed p-forms on such an F, and that complex has some additional complexity because, you know, F has some stackiness in it and some derived structure. So in particular, it's infinitesimal theory, it's tangent space. It's not really a sheaf, but it's a complex. And that complex, so the smoothness that I was alluding to is just saying that that complex is a complex of vector bundles locally, and a finite complex of vector bundles locally. But because we have this internal differential in the tangent complex, and you also have the Derived differential on forms, the forms on this space are really a double complex, and these closed p-forms are just cocycles in the total complex of this double complex. And so formally, when you write it down, what you really need to do is you need to take the pit step of the Hodge filtration. So this is the second bullet point. You need to take the pit step of the Hodge filtration in the Derived algebra for the cotangent complex of this F, and take the total complex, but with respect to the product. So these are infinite double complexes, so you need to complete when you're totalizing. And so a cocycle in this complex, say if we do form degree 2, a cocycle in the complex of closed two forms is going to be a closed two form, and because we are dealing with the complex, you actually can take a cocycle in any homological degree, so you can shift that complex by n, and you can take an n-shifted two form, which is just a degree n cocycle in this complex. And if you have such an n-shifted form, closed two form, so you can contract the tangent complex with it, and that's going to send you to the cotangent complex, because it's a two form. It's going to send you to the cotangent complex shifted by n. And you can call the form non-degenerate if that contraction is quasi-isomorphism. So that gives you the notion of a shifted closed non-degenerate two form, so gives rise to this shifted symplectic geometry. So these are the guys that we're interested in, and of course if your derived Artin stack is just a space, smooth space, then the tangent complex is just a vector bundle, and this is just an ordinary algebraic symplectic form. But if it's not a space, then you get this extra fuzzy. Okay, and let me just say there is so this type of symplectic geometry comes with the full package of what you know and understand in ordinary symplectic geometry. So if you have any map of derived stacks, you can talk about, and the target is symplectic, you can talk about isotropic structures being specified on the map. So if the target is a n+1 shifted symplectic guy, an isotropic structure will be a way to trivialize that n+1 shifted symplectic guy when you pull it back to F. And because again we are dealing with a space of forms or a complex of forms, trivializing means you need to specify a homotopy. So it means that you pull back the n+1 cocycle in the complex of closed two forms, and you want a homotopy between that cocycle and 0 on the source. That's an isotropic structure. And then you can talk about non-degeneracy of such isotropic structures. An isotropic structure is Lagrangian if, when you contract the relative tangent complex for the map, so that's like the normal bundle for the map, then you get the cotangent complex for the source shifted by f. And so there is an interesting feature that appears here, which is that it's a little bit, these non-degeneracy conditions, they are interchangeable. So Lagrangian and symplectic structures in this shifted world are really the same thing if you put them in the right context. So you can start and develop the full theory just by talking about Lagrangian structures without mentioning non-degeneracy of symplectic forms, or you can do it the other way around. So this is this comment here, that if you have an n-shifted Lagrangian structure for a map from a stack to a point, you know, the point has only one symplectic structure, which is the form 0. But you can put it in any homological degree. And if putting a Lagrangian structure on the map to the point is the same as putting a symplectic structure on the source. These are just the same two pieces of data. And another thing that's worth mentioning, if you haven't seen this, maybe it will give you some sense of what's going on. So this derived stacks, as I said, they have tangent complexes, which are complexes of vector bundles, and these tangent complexes, they have pieces, homological sheaves, homology sheaves that sit in different degrees. They could be positive degrees, negative degrees, degree 0, and the stackiness of the underlying geometric object is encoded, so the infinitesimal theory of the stackiness is encoded in the positive degree homological guys, and the nilpotence, the derived structure is encoded in the negative degrees homological guys in the cotangent complex. And what the symplectic structure, if you have a symplectic structure and you have this extra fuzz that you need to resolve singularities, the symplectic structure actually exchanges those two. So you really need these extra pieces if you want to understand what symplectic is. Okay, so this is my crash course on shifted symplectic geometry. So now I'm gonna, maybe examples. These are really the cheap examples that you get without any thought, but they're useful. So if you have a reductive complex algebraic group and a non-degenerate invariant quadratic form on the Lie algebra, that gives you a two-shifted symplectic form on the classifying stack of the group. Because the classifying stack of the group has a cotangent complex, which is the dual of the Lie algebra placed in homological degree 1. So this wedge product is really the symmetric product of the dual of the Lie algebra. When you shift it by 2, it's literally the symmetric product. So this gives you, the killing form actually gives you a closed 2 form, and it's very easy to check that non-degeneracy of the killing form is exactly the non-degeneracy condition of that closed 2 form. So choosing killing forms on reductive Lie algebras is the same as choosing two shifted symplectic forms on the classifying stack of the group. So this gives you some collection of examples, and also you can get cheap examples by just taking cotangent bundles of, say, smooth schemes, and then putting the fiber of the cotangent bundle in homological degree minus n. And then the tautological symplectic form on that stack or derived space, depending on the sign of n, will be an n-shifted symplectic form. So these are somehow, as I said, examples that you get by just taking the definition and looking at the simplest possible way to implement it. Now, what I want to do, as I explained, was I wanted to take a sheaf over a topological space of stacks. And I want to understand how to specify a closed form or closed form along the fibers, and then how to state that that form is non-degenerate, relative. And you can actually do it with arbitrary sheaves on a topological space of stacks, as long as the space is locally compact. The whole theory works, and in fact in the paper we are writing we do both. We do the general theory, and we do the specific theory. The problem is that if you do it with arbitrary sheaves on locally compact topological spaces, you cannot compute anything. So if you want to compute things, you have to restrict the type of spaces and the type of sheaves, and somehow the best universe in which you can do many constructions and computations is if you look at constructible sheaves of stacks on stratified spaces. So that's what I'm going to explain. So the good thing about constructible sheaves is that at the end of the day, once you fix the stratification, so these are locally constant sheaves of stacks on a stratified space, locally constant on the strata, and at the end of the day, if you try to understand the constructible sheaf, it's understood in terms of some combinatorial data. So before I talk about the constructible sheaves, the thing on the background that you really work with are diagrams of stacks. So this will be the hidden combinatorics that describes the constructible data. I'm going to start with an indexing category, which, in general, it's a finitely presentable infinity category, but in all the examples will be just a partially ordered finite set. So that's, in the examples, as you'll see, this will be the labeling set of our strata for the stratification. And I want to look at diagrams of objects in some category, C, that are labeled by my indexing finitely presentable infinity category. So this will be just functors. So diagrams of shape I in C will be just functors from I to C. So collections of objects in C and then arrows that are given by the arrows in I. And I'm assuming that the category I'm working with has finite limits. So in particular, I can look at global sections of a diagram. It will be just the limit of all the objects in the diagram. Now, because I want to do forms, there is a little bit of homological yoga here. You cannot really label your form data by the original diagram. If you start with a diagram of spaces or stacks or something like that, and you want to understand the forms on that, because the forms behave contravariantly while the space behaves covariantly, you have to keep both directions in the labeling set. So the way to do that, it's well understood in homological algebra, you need to take the category of twisted arrows in your labeling category. So the category of twisted arrows, if you haven't seen it, it's something very simple. So the objects are just the maps in I, and the homomorphisms between two maps are like, it really looks like a category of maps in the category I. The homomorphisms between two maps are commutative diagrams, but the direction of the top arrow in the commutative diagram on the source is reversed. So they go forward on the bottom, on the target, and go backward on the sources. And this thing is composed in the obvious way. And so if you have the category, so if you take the category and you take the category of twisted arrows, of course you have a target and source functors to the category I and to the opposite category. And now you can use that to actually construct forms. And it's actually a little bit useful to use the full flexibility of the theory. So I'm going to look at not just forms on the diagram of spaces I'm dealing with, but I'm going to look at forms with coefficients in some prescribed complexes of vector bundles. So I'm going to fix a diagram of complexes of vector bundles labeled by I, and a diagram of stacks labeled by I. And then I get a functor of forms, which takes a twisted arrow and sends it to the p forms on the stack labeled by the source of the arrow, with coefficients in the complex of vector spaces labeled by the type. And the actual complex of p-forms is going to be the limit of all those guys over the twisted arrows. And so this gives you a good theory. This has pullbacks, it's push forwards, it behaves really well. So the space of closed forms is going to be just the topological realization of the dot-Kahn construction on this complex. And you can think about a closed p-form on the diagram of stacks or spaces F with values in the complex diagram of complexes E as just a connected component in this topological realization, or as a degree 0 co-cycle homology class in this complex. And you have a global section functor which takes the complex and maps it to the closed p-forms on the limit of the diagram of spaces with coefficients in the limit of the global sections of the complex, the diagram of complexes. Now, to explain how this gives you a good notion of forms on constructible sheets of stacks, I'm going to talk about co-specialization. So the key to understanding constructible sheets of stacks in terms of diagrams is to use the command. So let me just recall the standard command for topological spaces. So if you have a nice topological space, X and a closed subspace Z and then a complementary open U, and you have any nice value category, and now I'm going to assume it has both limits and co-limits, then a sheaf on X with values in C can be assembled completely out of a piece which is a sheaf on the closed and a piece which is a sheaf on the open. So the way it works is you take a sheaf on X with values in C, you can restrict it to the closed, you can restrict it to the open, so you get two of those guys. And then use the unit of the junction between the pullback and the push forward for the open immersion, and you get a co-specialization map, a gluing map from the restriction of the sheaf on the closed to the restriction of the sheaf on the open, extended, a pullback extended by 0 to the whole thing, and then pull back to the close. And knowing this co-specialization, so knowing the sheaf on the open, the sheaf on the close, and the co-specialization map actually gives you the original sheaf uniquely. So there is an equivalence of infinity categories, which says that the cone of this functor, so the lax op limit of the functor from sheaves on the open to sheaves on the close, is exactly the sheaves on the whole thing. So this is what you use to reduce constructible sheaves of stacks or objects in some reasonable category to combinatorial data. You can apply this to the strata in a stratification. And it will give you the description of the sheaves of stacks, and it will also give you the description of the forms. So suppose that we have a good stratified space, and I'm not going to explain what good is. So these yellow things are, if you click on them, actually there is an explanation. You can go look at the slides. So suppose that you have a nicely stratified space, and you have I is going to be the finite partially ordered set that labels the strata of X. So being good will mean in particular that the stratification is finite. And then for each alpha in I, X alpha will be the stratum labeled by X alpha. And now you can look at sheaves, say, of topological spaces or simplicial sets, which are constructible for the given stratification. So locally constant sheaves of simplicial sets on each stratum. So for each stratum you have the restriction of f on x alpha, so it's a locally constant sheaf, but also constructible sheaf. And now you have nearby cycles for such sheaves, which are nearby each stratum. So if you fix a stratum and a sheaf, then you can choose any closed subset which contains the stratum as an open. So for instance, you can take the closure of the stratum. And you can take the complementary open. You can take the nearby cycles for your sheaf for that open close recommand and restrict it to the stratum. Then you get the co-specialization map, which is the restriction of the co-specialization map for the open close recommand, a very easy, just staring at this definition for a moment tells you that argument tells you that this does not depend on the choice of z. It only depends on the stratum, so you get this well-defined sheaf of nearby cocycles or cycles of f nearby for the stratum, and you get the co-specialization map. Except that this co-specialization map is the one that's coming from all the closures, right? So it's like integration of all standard co-specialization maps of points that are in the closure of the stratum. But yeah, so for every constructible sheaf, you get the value of the sheaf on the stratum. You also get the nearby fiber of the sheaf on the stratum, and you get the co-specialization map from the value of the sheaf on the stratum to the nearby cycles. And this data actually, again, combinatorially reconstructs the whole sheaf. So it makes sense, this all makes sense not just for sheaves of spaces, of topological spaces, but makes sense for sheaves with values in any category that has finite limits. So if you have a finite poset labeling a stratification, you can look at the category of exit paths for that stratification. So it's some infinity category of paths that start in a stratum and go to a stratum which gets this one in your closure. And if the stratification is good, then this category is finitely presentable, and you can define. In fact, so there is a little theorem which you can find in Jacob's Topos theory book, which says that the constructible sheaves of spaces on X for the stratification are just diagrams of spaces labeled by this category of exit paths. And so for any category with finite products, you can define now the constructible sheaves with values in that category as diagrams labeled by the category of exit paths. And those are the I-shaped diagrams, and those are the C-valued constructible sheaves. So now let's start with one of those guys. You have all the standard features a sheaf will have when it's a sheaf of spaces. So if you have a point in your stratified space, you have all the paths emanating from that point, and you have the zero path, so that gives you an object. The value of the diagram on that object is the stalk of the sheaf at X. You have global sections, which is the limit over all the exit paths of the values of the diagram. You have an evaluation map from the global sections to the stalk. And if you fix a stratum, then you can actually describe explicitly what it means to have a locally constant object on your stratum. The fundamental group point of the stratum is actually a full subcategory of the category of exit paths. It's just spanned by all objects Ix, where X runs over the stratum. And you can define the value of F on X as the restriction of F to that subcategory, and then the fundamental group point actually acts naturally on it. And and that's what the locally constant guy is. And you can also define nearby cycles. So you can look at all paths that end in your stratum, or you can look at all paths that are non-contractible and end in your stratum. And the nearby cycles are just the extension of the values of your diagram on all paths that end on your stratum and not contractible, and the map to all the paths that end on your stratum. So again, it's a purely combinatorial algebraic description. And you have these nearby cycles guys, and you have the co-specialization map, which is coming from the unit of the right kind extension. So I'm going to call this the sheaf nearby cycles and co-specialization map. Okay, so now we can talk about forms. If you have a nice stratified space with strata labeled by a poset, and some exit path category both I, and you choose a complex of vector spaces on that space, which is constructible, and a complex and a sheaf of derived stocks, which is constructible, then you can define the complex of forms with values in E for the corresponding diagram and call it the complex of forms for the sheaf. You can also sheafify that, but it's not really important because we're going to be looking at forms for the whole sheaf, so you can just take elements in that complex. You have a global section map from the complex of evaluate P-closed forms on the sheaf, relative forms on the sheaf, to the absolute closed P forms on the global sections of the sheaf, times the cohomologies of your complex of vector spaces on the space X. So coming back to F, the requirement that F has to be geometric, if F is a constructible sheaf of Artin stocks, and so they have to be derived Artin stocks, locally finite presentation, so that they behave like smooth guys, then for any local section of the sheaf of Artin stocks, I can look at the relative tangent complex. It's going to be a complex of vector spaces locally defined on the stratified space X. And if I have a relative closed form on the sheaf with values in a complex of vector spaces C, I can pull it back by this local section, and I'll get a skew-symmetric p-fold pairing on the pullback tangent complex with values in the complex of vector spaces E. And you can think about this as the value of the form on the section Z. So now I can talk about, so this is what a closed form is, and closed forms have values, and now I can take this and explain what non-degeneracy means. So start with the stratified space, which is good, and I'm going to also assume that the strata are equidimensional so that I don't have to come and correct my combinatorial formulas the whole time. Take a constructible sheaf of nice geometric stocks, and I'm going to take the coefficients now to be not an arbitrary complex of vector spaces, but they're going to be the Verdier dualizing complex with some shift, where the shift can be anything. So it cannot be arbitrary, it has to be the dualizing complex, but it could be a shifted dualizing complex. And here's the definition. The complex and space of relative and shifted forms on the stack F is going to be the complex of closed relative P forms on F with values in the dualizing complex shifted by F. And in particular, a relative and shifted 2 form on the stack is going to be relative. So this is 2. It's a relative 2 form with values in the Verdier dualizing complex shifted by N. And it's symplectic if this value guy, the contraction with it of the tangent, the pullback of the tangent complex relative tangent complex bisection to the relative cotangent complex, mapping to the restriction of the dualizing complex to the open shifted by n, if this is a quasi-isomorphism for every section. So this codifies what I said, that we need to use duality on the base. So you cannot just naively say that relative tangent complex pullback is dual to the relative cotangent complex, because dual for complexes of vector space on the base means tensor with the dualizing sheaf. So you need to keep this as part of the data. And as I promised, you can actually write everything combinatorially. So in particular, this non-degeneracy condition, which is the condition for all opens and all sections, and it's kind of K, it actually has a finite incarnation. You can write it down explicitly in terms of combinatorial data. Once you describe your sheaf of spaces as a diagram of spaces and your form as a diagram of forms, you can say what it means for that diagram of forms to be non-degenerate. So what happens is that, so if you have a sheaf of spaces, constructible sheaf of derived stacks, and a diagram, and a relative n-shifted 2 form, closed 2 form, then that form actually induces an absolute form, shifted closed form, on the nearby cycles on each stratum. It's absolute and it's shifted, but it has a different shift. So this shift is coming from the fact that everything had values in the dualizing sheaf. So it's an absolute form with a shift of n plus 1 plus the dimension of the stratum. And not only that, but it induces an isotropic structure on the co-specialization map from the value of the sheaf on the stratum to the nearby cycles. And the first theorem is that the relative 2 form on the constructible sheaf of stacks is symplectic, if and only if for every stratum this absolute 2 form on the nearby cycles is symplectic and the co-specialization map is Lagrangian. So it's a thing that you need to check once for each stratum for the combinatorial data that describes your sheaf. Right? The combinatorial data that describes your sheaf consists of all the values of the sheaves on all the strata, all the nearby cycle values on all the strata, and all co-specialization maps.
So for these absolute forms do not glue?
They glue, but they glue in this relative guy. I mean, so in fact, if you take these absolute forms, they're a little bit less data than the relative guy. But their non-degeneracy it captures completely the non-degeneracy of the relative guy.
Can you use this theorem the other way around to put restrictions on possible stratification such that the sheaf becomes constructible? Like if you know already that.
Say it again.
So I guess I'm saying that you're describing a way to check.
That something is non-degenerate.
Yeah, right. But I was wondering if this can also be used the other way around. If I have a sheaf and I want to describe stratification according to which it's constructible, but I know already it's symplectic, this probably will put some restrictions on like how many strata the stratification has to have or what dimensions they must be.
Yeah, but you know, I mean, you still need to be able to write data for your sheaf. I mean, you know, if you start with an arbitrary sheaf on a locally compact space, you still need to be able to compute the nearby cycles for closed and opens. And then, of course, yeah, I mean, this will give you some restriction on the type of strata, but I don't know if you can actually do anything with it. It's possible. Okay, but the push-forward theorem that was promised in my title. So here is the great thing about this. You can push forward. So you can get many new examples from examples that you understand. So if you have a stratified space of nicely stratified map between nicely stratified spaces, and you have a sheaf of stacks on the source and a sheaf of vector spaces on the source, a complex of vector spaces, you can push forward the sheaf of stacks to get the sheaf of stacks on the target, and you can push forward the complexes of vector spaces to get the complex of vector spaces on the target. And again, in terms of diagrams, these are just very easy CAN extensions. And if you have a relative form, oops, if you have a relative form on the guy upstairs with values in E, then you can push it forward and you get a relative form on the push forward of the family of spaces with coefficients in the push forward in the family vector spaces. And the theorem is that this preserves non-degeneracy, preserves symplecticity. So if you take a proper map between stratified spaces and you take a non-degenerate two-form with coefficients in the dualizing sheaf, you can push it forward, and then you can use the trace map between the dualizing complexes to get actually n-shifted two-form on the push-forward family of stacks. And the claim is that if the guy upstairs is symplectic, the guy downstairs is symplectic. So this gives you, for instance, by passing to global sections, right? I mean, if X is proper, you can just take them up to a point, get the push forward is just taking global sections. This gives you ways to compute, to produce new symplectic forms from relative ones that you understand. And let me just, I'm going to click on this one, to say that essentially all constructions that we know in shifted symplectic geometry are special cases in this theorem. So if you do this for constant sheaves, so take a topological space, which is just, you view it as a stratified space with a single stratum. Take a sheaf of, take a derived stack and look at the constant sheaf with values, with fiber that derive stack. Then take an absolute closed and shifted two form on your derived stack. You can interpret it as a relative form. Just have to remember that so it's a relative form with values in the constant sheaf shifted by n. But the dualizing sheaf, if X is an oriented manifold of pure dimension D, the dualizing sheaf of that manifold will be the constant sheaf shifted by D. So if you want to interpret it as a relative form on the sheaf, on the constant sheaf, it's going to be a relative form shifted by n minus D. And so omega is non-degenerate as an n-shifted absolute form on F if and only if omega x is non-degenerate as a relative n minus D form on F. And the push-forward theorem tells you that the trace of the global sections of this guy is an n minus D shifted symplectic structure on the global sections. And the global sections are just the maps from X to F. So this is this algebraic version of the AKSE formula, which says that the mapping stack from something which is oriented, which is calabial, to something which is n-shifted symplectic, is n minus D shifted symplectic. So it's just a special case of this push-forward theorem applied to the constant sheaf. You can say what a Lagrangian map is by using the push-forward theorem. This is what this chicken and egg thing I was mentioning, that you can use one to define the other. So if you take your topological space to be the half-open interval, and stratified by the open interval as an open stratum and the right end as the closed stratum, then sheaf of stacks on this stratified space is just two stacks, one value, one value at the closed stratum, one value at the open stratum, and a co-specialization map. So in fact, the value at the open stratum is also equal to the nearby cycle, so because there is nothing that contains this in the closure, in its closure, so it's just one co-specialization map from the closed to the open. The dualizing sheaf is the extension of the constant sheaf from the interior shifted by 1 by 0, and then a relative n-shifted symplectic structure is what the Lagrangian structure for this map is. It's an n plus 1 shifted symplectic form on the interior and a Lagrangian structure for the map. Lagrangian intersections are a special case. So if you take a closed interval and you stratify by the open and the two ends, then a constructible sheaf of stacks is specified now by 3 stacks, 2 guys at the two ends and 1 in the interior. And there are two co-specialization maps, one going from the left end to the interior, the other going from the right end to the interior. The dualizing sheaf is still the extension of by 0 of the constant sheaf shifted by 1 from the interior. And an n-shifted symplectic structure relative from this sheaf is an n+1 shifted symplectic structure in the interior, a Lagrangian structure for this map, a Lagrangian structure for this map. The push-forward theorem, so if you take this guy and you push it forward to the point, tells you that the global sections are n-shifted symplectic, and that just means that if you look at the global sections are just the fiber product of these two Lagrangian maps, the Lagrangian intersection, and it tells you that this is an n-shifted symplectic structure. So this is the Lagrangian intersection construction that we had in our hot paper. It's again a special case of this theorem. Hamiltonian reduction, being a Lagrangian intersection, is a special case of this theorem. So if you take a closed interval with the same stratification, if you fix a linear algebraic group and a coadjoint orbit, and any symplectic algebraic manifold with a Hamiltonian G action, then G equivariant moment map is just the statement specifying a G equivariant moment map is just specifying a map from M mod G to G dual mod G, saying that this is a G equivariant moment map just says that this map is Lagrangian. So a sheaf on this interval with various derived stacks you can concoct out of this data is at 0 you put the coadjoint orbit modulo G, at 1 you put M modulo G, and in the interior you put G dual modulo G, which is really the cotangent bundle of BG shifted by 1. So these natural maps from the coadjoint orbit modulo G to G dual mod G, or the moment map, they're Lagrangian. And so this gives you a relative symplectic form. A relative zero-shifted symplectic form. And the push-forward theorem tells you that the trace of that is a zero-shifted symplectic form on the global sections, and the global sections are exactly the derived Hamiltonian reduction. You take the derived fiber of the moment map over the coadjoint orbit and you quotient by G. So this is the Kirov-Kosten-Surel form in this algebraic context.
G is finite dimension.
G is a linear algebraic, finite dimensional linear algebraic. And you can also do quasi-Hamiltonian reduction. So this, here you take the two-sphere as a stratified space, and you stratify it by 3 strata, the north and the south pole, and the complement, the cylinder. Now take a reductive group. It can be arbitrary, it has to be reductive, and take a conjugacy class. And suppose that we have an algebraic symplectic manifold equipped with a quasi-Hamiltonian G action, so we have an equivariant group-valued moment map. And again, we get a constructible sheaf of stacks. It's the conjugacy class mod G, the manifold mod G, and on the interior we get BG. And so, because on the interior we get BG, we need G to be reductive so that we have a symplectic form here. And so the maps, again, are Lagrangian, and the dualizing complex is the extension by 0 from the cylinder of the constant sheaf shifted by 2, and the standard two-shifted symplectic form on BG, given by the killing form, extends to a natural relative zero-shifted symplectic form on the whole thing, and the push-forward gives you the quasi-Hamiltonian reduction, the derived quasi-Hamiltonian reduction. So all of this is to say that there is this theorem which you should think about some combinatorial generalization of quasi-Hamiltonian reduction. It's which symplectic forms can you assemble by taking symplectic forms on pieces and maps between them that happen to be Lagrangian, and then taking fiber products and deeper fiber products and deeper fiber products and deeper fiber products. So this actually records all of this data. How are we going to try? Wow. So I'm going to talk about the Stokes data now, explain how this actually describes for you the Poisson structures on the moduli of Stokes data. In fact, in any dimension, but I'm not going to have time for a higher dimension, so I'm just going to do the case of curves. and described as symplectic limits. So, the case of curves, suppose that X is a smooth topological surface, and we're going to think about it as something underlying projective curve minus finitely many points. And we're going to stratify it. It's going to have two open strata, an inner one and an outer one. The inner one will always be connected, the outer one may be disconnected. And then there will be one-dimensional strata, which will be arcs, and they'll be labeled by some set E, and then there will be zero-dimensional strata, which will be points, will be labeled by some set V. And the certification has to be nice, tame, so two arcs meet exactly at one endpoint. Each arc separates the inner and the outer open strata, and the outer open stratum retracts on the boundary. So this is the picture. So X is the surface, the inner stratum is this blue thing, the outer stratum are these yellow cylinders that go near the punctures. The one-dimensional strata, so there are these circles here that separate the inner and the outer stratum. They're near the boundary. And we've broken them into arcs by points. So these arcs are the red ones are the one-dimensional strata, and the green points are the zero-dimensional strata. And so I'm going to look at special sheaves of derived stacks on this stratified space. So they're constructible sheaves of derived stacks, which are uniquely described by properties, by what their values on the various strata are and what the co-specialization maps to. So for the two-dimensional strata, for the inner and outer open stratum, I will require that the value of the sheaf on each stratum is the classifying stack of a reductive group G. And the groups will be different on the different strata if you want to describe Stokes structures. But they're going to be reductive. And on the arcs, on the one-dimensional strata, if you take an arc XE and a point in that arc, then the arc separates the inner stratum and the outer stratum. So the specialization of stratum, the fact that the arc is in the closure of X inner and a closure of X outer, gives you co-specialization of stacks. So it has to send whatever we put on the edge to whatever we've put on the inner stratum and whatever we've put on the outer stratum. And remember, on the inner stratum I have put B of G, which is some reductive group, and on the outer stratum also B of some reductive group L. So the condition on the sheaf is that on the edge I have to put B of P, where P is a parabolic in G and L is the levy of that parabolic. And the maps are induced by the inclusion of the parabolic in G and by the levy quotient. And for a point, you have specializations, the point is in the closure of the two-dimensional strata, in the closure of two one-dimensional strata, and so you have co-specializations from the stuff that sits at the point to the open guys and to the edges. And the requirement is, so on the inner stratum we have BG, on the outer stratum we have B of a levy, on the one of the arcs we have B of a parabolic, on the other arc we have B of a parabolic, and at the point where the two arcs meet you have to put P, B of the intersection of those two parabolics. So you see that there is one condition here that's implicitly assumed, which is that the levy that we have on the outer stratum for the two arcs that meet at the point and separate the outer and the inner stratum, that levy is the same for the two parabolics. So the two parabolics that sit on this, so if you have parabolics on each of these arcs, these parabolics that go on this circle, they cannot be arbitrary. They're all parabolics with the same levy, with the levy that sits on this yellow. Okay, so This actually describes a constructible sheaf. The data that describes it is a bunch of parabolics for each neck, and they're all parabolics with the same levy, and then that levy lives here on the neck, and you know it's a sheaf of levies which may or may not be constant. It's locally constant, but not necessarily constant because this thing is not simply connected. And in fact, the sheaf of G's on the interior need not be constant. It could be only locally constant, but in most of the applications we'll take it to be constant. But these guys here definitely will not be constant. Okay, so here is the theorem. If you have such a sheaf, then the restriction map from the closed two forms with values in the idealizing sheaf for this stratified space to the closed two forms with values in the idealizing sheaf on the inner stratum, just on the blue guy. It's a homotopy equivalence. So choosing a relative closed two form here is the same as choosing a relative closed two form on this locally constant or constant sheaf. And if you take a form here and you extend it, if you take a form on the interior and you extend it to a relative form on the whole thing, then non-degeneracy is preserved. If this guy is non-degenerate, then this guy is non-degenerate, and vice versa. So this gives you a way of constructing non-degenerate forms as long as on the inner guy. So, for example, if the inner guy is constant, it was BG, and BG has a shifted two form. And if it's locally constant, you need a shifted two form which is invariant under the fundamental property. So this gives you a way of constructing forms if G is because G is reductive, and so you get a relative two form on this type of sheaf. And the point is that such kind of sheaf actually controls Stokes data for local systems on your curve. So if you have a smooth projective curve over C and you remove finitely many points and you fix irregular types for connections, G connections near the points, so these are like Laurent tails for the poles of the connection without the residue, with degree bigger than less than -2, less than or equal to -2. Then this actually determines a Deligne-Malgrand Stokes sheaf. By this theorem of Deligne-Malgrand, Stokes filtered local systems controlled by the parabolics that the Deligne-Malgrand Stokes sheaf gives you classify exactly local systems with Stokes data of irregular type I, given by these Laurent tails. So the global sections of this Deligne-Malgrand Stokes sheaf on the surface with boundary that you get by blowing up the points to introduce the boundary are exactly the Stokes filtered local systems of the modular Stokes data from this irregular type. So it's a global section, so if you want to understand why this thing is Poisson or symplectic, you need a symplectic structure relative along the fibers of this guy, and this is what we were doing, the constructed one. And oh wow. And so the point is that for any Deligne-Malgrand Stokes sheaf, so for any guy for which this relative form is defined, so for example the group on the interior is constant and we've taken the killing form, then we actually get a symplectic structure on the modular space. So if you take a Deligne-Malgrand Stokes sheaf of stacks, which is equipped with a relative two form, the way we constructed it, you can take your surface and map it to the half-closed interval. So it's a stratified map which collapses everything in the interior to 1 and projects each cylinder, each neck cylinder to the open interval 0, 1. It's a proper stratified map, And if you take the push forward of the relative symplectic form, you get the symplectic structure on the push forward start. And if you analyze what you got really by writing the nearby cycles on the open stratum and the value on the open stratum, you got a Lagrangian structure of the sections of your Deligne-Lagrange Stokes stack on the outer, on the cylinders. So a symplectic structure here and a Lagrangian structure of the map from the interior. And this is exactly the moduli of Stokes data. So the G-local systems of Stokes data of irregular type I are exactly these sections. And the local systems on the boundary with formal monodromy given by the associated gradient with the Stokes filtration are exactly these guys. So we got a Lagrangian structure on this space. This is symplectic, this is Lagrangian, so that means that this guy is Poisson. So that's the standard statement that the moduli of Stokes data is Poisson. Only now you don't need to do any qualifications. You don't need to take the Stokes data to be stable. You don't need to take the part of the moduli space to be smooth. It works for all Stokes data and it works for the whole moduli space. And because this is Lagrangian, if you fix the formal monodromy, so if you fix a Lagrangian here, which is conjugacy class of elements in the local system of Levis, and you take the Lagrangian intersection, you'll get something symplectic. So that's the other standard statement of, say, Blauch and Yamakawa, saying that moduli of Stokes data with fixed formal monodromy are symplectic at their smooth form. And I'm going to shut up.
So this is sort of algebraic step.
Everything is algebraic.
If I want to compare with a similar symplectic stack or Poisson stack on the drum side, I need to extend this.
Well, yeah. So this is the better picture. I mean, you could in principle talk about the derived version of that. We haven't done it because it's not as combinatorial as this one. But there should be a derived version and there should be a Riemann-Hilbert correspondence, but it's going to be much simpler. I mean, there is a little bit of the derived version that we did, but not in this generality with the Pushforward Theorem. So in higher dimensions, Bertrand and I, we worked out the Poisson structures on the local systems on a non-compact smooth variety in this language, and it's kind of tricky because you need to work with a bunch of formal neighborhoods, which you can only do non-commutatively. So it's a slightly different theory, but yeah, there should be some Derived counterpart of that for sure.
So can we pull back instead of push forward?
You can pull back, but you know, the pullbacks, because these are relatively symplectic guy, pullbacks are for free symplectic. That's not.
So if I have this relative symplectic structure for the total space of this vibration, I can always
pull back the vibration, pull back the symplectic form, it will still stay relatively symplectic.
No, not staying relatively symplectic. I want to construct absolute symplectic structure from a relative form.
No, because pulling back something relative, it's still relative. I mean, the thing that makes something relative absolute is passing to cohomology of global sections. Yeah. Pulling back doesn't make relative things disappear.
Yeah, actually, this for case of J, irregular data, one can have a different picture because this data with these sheaves is certain macro level support. You can move certain curves, oriented curves.
Mm-hmm.
And this is a general, more general factor. You consider any weakness stratification or any weak thing, oriented manifold, then we get derived Poisson structure on model space, which you probably didn't want to have. If you consider the structural shift on oriented manifold, stratification, the model space of object will be shifted to Poisson. and the one where you respond to like consider this single Lagrangian skeleton. It's infinity gets Lagrangian skeleton of one less dimension, and here to get relative to symplectic structure.
Is it true for any step of the object take it there?
Yeah, it's part of very general story. If you go from any group to J, it belongs to
Yeah, I just didn't get the statement.
No, I've considered model stack of constructible sheaves
Okay.
of vector spaces, dimensional, of even with stratification.
Oh no, no, I got the statement now. Yeah. So you're doing the non-commutative version of what I'm saying.
Yeah.
No, yeah, we haven't done that. Yeah.
Other questions? Well, it's not. Let's thank Toën again.